Turn my camera off.
Oh, keep your camera on. Hi, everyone. We're just going to get started in about 1 to 2 minutes and let some more people join here. See the numbers ticking up there. All right, I think it's time to get started now. Good morning, everybody. We are very excited to have Tom Nations with us today for our Introduction to Snap course. As you guys know, this is a 3-hour course going from 9 until 12 Central Time or 8 to 11 Mountain Time. But we'll have some breaks throughout, so not a problem there. If you guys have any questions, we do also have Daniel on the chat from Whitson, so he will be able to help answer questions as Tom is presenting, or if you're looking for something that you can't find, he's got your back there. And if you are looking for any more information on Snap or our Whitson products, please never hesitate to contact our team at support@whitson.com or snap@whitson.com for Snap specific questions. Before I hand it over to Tom, I do also want to say that I sent an email last night to everyone registered for this course with the Snap project files. Please make sure that if you are going to be following along with the exercises, that you have that downloaded. It's a zip folder, so you'll just need to extract that and you'll be good to go. And I will try to add it into this chat as well, but it's not letting me add a folder. So I will work on that as Tom gets started here. And great to have you all here. Tom, it's all yours.
All right. Thank you, Jessica. Well, good morning, everyone. As you know, my name is Tom Nations. I've been in the gas lift business for about roughly 50 plus years, and I've been working with the Snap application since, let me think back, the mid-90s, I think, something like that. So anyway, so we'll get started here. This is a little introductory slide here, and I'm going to explain a few things about Snap, and then we'll go start into what some of the capabilities are. So Snap is it's basically a nodal analysis program. It started out that way, and then over the years, we have added in other modules, specifically gas lift, which is the one that's probably used the most, and in jet pumping. So as this slide says, advanced modeling supports rigorous multi-layer IPRs. We have 12 different hydraulic correlations. Of course, we do gas lift and jet pump design and optimization and troubleshooting. And we also can hook Snap up to your engineering database with a little extra work, but can be done. So here's some of the things that we're going to talk about today. Gas lift design and troubleshooting, generating performance curves, VLP curves, etc. Valve spacing, how to diagnose and troubleshoot an existing gas lift design, run sensitivity analyses on different things. In different nodal analysis designs, you can analyze different things, and I'll go over all those as we go through the introduction to Snap. But things like system sizing, tubing size, wellhead pressures, all that kind of stuff. And then jet pump, the power fluid. We use both water and dead oil for power fluid, as you know, probably. And we'll get into that as we show an actual jet pump design. And comprehensive analysis, we've got all the, all the features and stuff in any nodal analysis package. Industry standard, we've got 12 different hydraulic correlations. We can link to ODBC databases. We use nodal analysis to optimize production rates and advanced segmentation. We predict future schedules, and using pressure transient results, we can predict what your well is going to do if you add artificial lift to the system. And here's how you can get in touch with us. Okay, so without any further ado, I'm going to go ahead and start with this. Let me get this one. Here's the first. Show you if I can drag this over here. Okay, come on. There we go. All right. So here's Snap. It's a Windows compatible application. It's written in Microsoft C++, so it has the same look and feel as many of your other Microsoft products. Excel, Windows, Word, PowerPoint, stuff like that. When you open Snap for the first time, and here's the title slide, the title of the slide up here. So the file name that we're working with right now is snap nodal analysis.snp. So all the Snap data files, we call them data sets actually, all have that file name extension .snp. And what you see here when you first open Snap, if you've not opened it before, you will get a default data set. And I'll show that one to you right here. It'll be right here, it says new data set. So this is what you'll probably see when you open Snap for the first time. So it's just a mostly blank data set with just a few things in it. And then to confirm that you have a working version, when you have this default data set open, if you do the calculation run, and there are 3 different ways to do that. Let me explain that to you. So you can calculate all, or you can push this red exclamation point. That's a calculate all, or depending on what kind of keyboard you have, it's F5 on your keyboard. And I think, yeah, mine's a little, my keyboard's a little odd, but anyway, so here's what if you just click this button here, you should get a couple of displays up. Here's your nodal plot, and here's an output, basic output report. So if you get these two using that default data set, your Snap app is running. All right, so I'm going to turn this one off, and I'm going to use this nodal analysis.snp file to walk you through all the inputs and options and stuff like that in Snap. So to get started, this is just a big icon. So the recommendation here is you neither maximize nor minimize this guy. He's going to get covered up, of course, with output windows and stuff like that. So, but he's always available in the background. And it's all these inputs, general, PVT, inflow, etc. These are the buttons that you can push to access that input dialog. The general one, for example, brings up this input dialog. But you can get to that same input dialog a couple of different ways. Under inputs on the toolbar up here, the drop down, and there's your general, PVT, etc., the same as on this big icon here. Then also on your toolbar up here, if you just float your cursor along that toolbar, you'll see the same input, we call them dialogues, input windows, input dialogues up here. The ones that are grayed out are the ones that currently don't have any information in them, so they haven't been switched on yet. We'll see how that works out as we go through the demonstration here. All right, so that's how you open any of the input dialogues. The other things on the toolbar, on the drop-down menus up here, here's all your file management applications. Again, just like any other Windows type program, it actually shows the last several data sets that I've had open, and yours, fill in as you go forward. But it's how you'd access your file management system. Again, just Microsoft type. Here's edit. We can do both. You can go to units, and we can go to either field units or SI units, and you can switch them individually, actually. So if you're working in some country where you use both oil field units and English units, then you can select and have those mixed as normal or as you wish. All right. All right. Okay, so that's that. And under edit, yeah, in new project preferences. Let me show you, go ahead and show you this right now, and we'll come back to this a couple of times during the demo. This is where you set all your machine specific selections. These things stay with the machine. They don't travel with the data files. So you can elect to show these things will always be the way you have your screen set up. So we'll look at those a little later. All right, then the other thing we have calculate. So calculate all, as I explained, that's the same as the red exclamation mark or as F5 on your keyboard. You can see just the IPR or just the hydraulics displays. But, Snap runs really fast. So, calculate all is a good thing. So here's this one. All right. So this is what we have in this data set right now. We're going to walk through some of the things that we can do, but I'm going to go through these other things here. So under the drop-down graphs here, this is where we get to some of the output stuff, graphical output stuff. So total system results, that's the nodal plot that you see right over here. So, and then you can show just the IPR. Now I'll turn that off. And then there's sensitivity results, flowing pressure gradients, and this is something we're going to talk about a little later, show you how to do different pressure gradient calculations. We can do velocity plots, some other things there. So those are there. All the graphs in Snap are based on a gradient report or a textual output. So it looks like this. So you've got depths, pressures, temperatures, and other things on this list. But the graph, this type of output is generated initially, and then this data is used to create any of the graphics. All right. There are several utilities, which we'll look at a little bit later, but view, toolbars, window, here's something. So on the window thing there, we have, using Snap, you're going to get a whole bunch of output dialog, output windows and stuff, and sometimes it gets a little confusing. So you can close them all wholesale or close them independently. When something comes back very quickly. So my recommendation is that you, on any of these output windows that you create, resist minimizing and resist maximizing these windows. If you don't want to see that one for a while, just turn it off and it'll come right back when you recalculate. It's really quick. And if you do get some lost windows, output windows or something, we'll get a call every now and then from somebody that says, I can't find my gas lift graph or I can't find my nodal plot. Well, what they've done is they probably either minimized it like this and it's down here at the bottom, or they've pushed it over completely onto another screen. And most of us have multiple screens nowadays, so that can happen easily. You can drag any of these output windows over onto the other screen, and then you forget you put it over there and it gets lost. So anyway, you can cascade or tile these windows to bring them all back into the Snap desktop. There's a couple of standard layouts here for the way we like, or way one of our users likes to present stuff, and one of them is the gas lift thing. So it will arrange all of your output windows in a certain order. Something about order of the way things show up on your Snap desktop. Any of the graphs or reports or anything like that, you can move them around anywhere you want. When you turn them off, oops, there I go, making it too big. Okay. If you turn it off and then tell it to come back, recalculate, all the graphs and reports and stuff come back in the same size and the same position on the Snap desktop as you left them. So don't worry about, can't see something, get it covered up with something. Just turn off what's covering up what you want to see, and then when you recalculate, it all comes right back. Reports window, here's the profile here. This is, who you are, and here's what your computer ID code is. That's what we need to build a license file for you, and just some information about who you are. And typically, unless you're in the VPC membership catalog with like these other people here, you're going to be everyone else. All right, so let's walk through some of the inputs on Snap here so you get a little familiar with how this works. And really you just start with the general input dialog. And some of the stuff well, just the title is a title, and there's no calculations go along with that. But we can analyze oil wells, gas wells, water injectors, and gas injectors, and simply by selecting this. So the two most used, actually the most used one is the oil well type. And then along with the well type, you're going to pick a IPR type. And here are all the IPR types that we have available. Vogel with reservoir data, Vogel with one production test, which you'll find typically is the one that's probably used the most because most of us don't have all the detailed reservoir data that's necessary to build the IPR using reservoir data. And then there's several other options down here, as you can see in this drop-down list. There's also a user IPR table. You can, if you have enough information to do that, you just select that and you get an extra tab up here at the top. Oops, additional hydraulic rates. Well, they'll come in at a later one. But typically, what did I have here? Vogel with reservoir data, I think is what I had. Let's see. Yep, maybe. All right, so back here again. Now, the other things we can do, this says not calculated for the completion type. You have to pick a reservoir, an IPR model that will allow you to put that in there. But again, most of us don't have the details necessary to fill this out. If you wish to look at one of those, you can certainly do that. Go to one of these, and it will, as we go through inputting stuff in each of our input windows, input dialogues, the next one may change depending on what you have selected previously. We can choose to include flow line in our analysis or not. We can do a jet pump analysis, and we have a plunger lift button here, but it's not active yet. So just pretend that's not there, I guess. Here's the ones that typically will get used the most: basic gas lift and detailed gas lift. So basic gas lift will give you just a very simple gas injection pressure and a flow and gradient curve to allow you to visually see if you can inject your lift gas at a certain depth or not. If you select the detailed option, then you will get all of the, and we'll look at this later, you get all of the gas lift valve information, all the valve details, set pressures, depths, AP-AB ratios, all that stuff. All right. Then, of course, we do need wellhead temperature and pressure for doing an analysis. So there are a couple of other tabs up here at the top. There's additional hydraulic rates, which I'll talk about in just a minute when we look at the nodal plot, and then optional input. So most of this optional input is for report headings and stuff like that, other kind of information. It's not much computational information on here. So that's basically the general input dialog, and you can simply just go next, and it brings up PVT properties. So we're going to use correlations down here for some of these things: solution gas oil ratio, oil formation volume factor, and oil viscosity. But you can, for any one of these, pick a table if you've got the lab data to do that. And just like before, another tab pops up so that you can put in that detailed information for that laboratory data that you may have. Otherwise, we pick one of these correlations to handle those types of things. You can do multi-zone PVT properties with SNAP. By selecting this, it gives you each one of those, and you can put in the values and the correlation types for each of those different zones you may have. And let me apologize now for my voice. I was on a trip last week, and I got a cold on the way back, and so my voice is a little gravelly today. So please excuse that. So anyway, we'll go back to just correlations here, and data here: reservoir temperature. This is hydrocarbon specific gas gravity. This is your produced gas, and whether you have any CO2, H2S, or nitrogen in the mix there. formation gas-oil ratio. Does not include your lift gas. This is just your formation gas. Calculate this GOR. Your oil API gravity, of course, and water-specific gravity. And I thought that was 107 before, but the total dissolved solids and the water-specific gravity are tied together. So if you know either one of them, you can, it will populate the other side. Oops. Like this. And then the correlations, of course. Then over here we have optional PVT table. So if you have laboratory data for any of these items, you can select that item. A new tab will show up and allow you to input that data if you have it. All right, that's PVT properties. All right, so next is our wellbore. Now, this is an important part of our analysis. This is going to describe the flow conduits that our reservoir fluids are going to be flowing up the well through. So these are the tubing IDs, casing IDs, liner size, and stuff like that. So what we have here so far is in this model we have tubing flow. Now we can model several other things: annular flow, tubing plus annular flow. So for example, if you have a new well, you start it up, it's flowing up casing, that's fine. You'd use tubing flow for that and describe the ID of the flow conduit as the ID of the casing. When you put the tubing in, then you've got annular flow, and that changes what the required inputs are. Of course, you have to have, for that, you'd have to have tubing OD, casing ID, and to describe that annular flow conduit. A lot of people are using annular flow nowadays, so that's why I wanted to talk about that just a little bit. The other one is complex flow. That's if you have multi-layer reservoirs and you run your tubing in there and across multiple perforations. So you have 1,000 feet of perforations or something, and you want to know where's the best place to hang your tubing tail for the most production rate. So you can choose that complex flow model, and it will allow you to put in the information where upper perforations might flow into the annual area, down to the tubing tail, up in the tubing tail, and then other perforations below the tubing tail will flow into the liner or casing below and up, and then the snap combines all those flows together. You can put your data in MD versus TVD, which is the most common I've found, or MD versus angle or TVD versus angle. Wellhead temperature and reservoir temperature. Wellhead temperature is brought forward excuse me, from the first input general panel. You can select to have these things for each segment, or do rigorous heat transfer, which is rarely used, but it's available. Here's where you pick your hydraulic model. Here are all the different ones we have: Hagedorn Brown, Norkaszewski, Duns, Ross, Aziz. Most of these are, well, let me say it this way. These are mechanistic, the ones at the bottom. Stoysits and Ansari and Choksi. Those are mechanistic models, and meaning that they didn't go out and measure anything. It's just pure math that they used to create these models. All these other ones, and by the way, these are in sort of like date order. This is kind of where, Hagedorn Brown dates back to the early 60s, and so is Duns and Ross and some of these other ones. The newer ones are here at the bottom, Ansari and Choksi, for example. So Hagedorn Brown is probably the most common one used, but not necessarily the right one. You got to pick the right one for your well. So looking at wellbore geometry, this is the flow IDs and stuff that our reservoir fluids are going to be transiting up, and this is the information that SNAP is going to use to create the flowing tubing gradients and these intake or VLP points on your nodal plot. In addition to that, we have a deviation survey tab here. You can put in, if you just take your deviation survey, put it into Excel, and put the MD and TVD depths, you can copy and paste from your Excel file into this grid to insert all your deviation information. The wellbore geometry, and the deviation survey holds thousands of data points, no problem. The wellbore geometry, however, will only hold 50 points. You can paste in more than that, but you'll have to trim it down by using this reduced segments here. The hydraulics are calculated based on, this is the entry point. SNP will always look at this wellbore geometry and say, okay, 100% of my flow is entering my tubulars at this, so be aware of that. You can put this all the way out to the toe of the well, but what you'll find is that the pressure difference between the heel of the well and the toe of the well is not dramatic. It's 20, 30 psi. Our laterals in our wells are actually very short pipelines. You can think about them that way. All right, so some other stuff on here. There's a standard pipe size here. If you can't remember that 2 3/8 tubing is 1.995, it's available here. This is basically a kind of a look at your Halliburton book, if not anything else. The other thing about inputting data into this wellbore tab is you can select a cell here and come over into this quick reference. Look over here and just double click the value and it'll pop over and into that cell. So that's one way to fill that out. All right, coming next, and I'm not going to talk today about well restriction and other stuff. Well restriction data is typically best put into your hydraulics here and put a line item in there if you have a nipples don't cause a problem, but if you have a joint of tubing that's undersized or pinched or something like that, you should probably add that to a line item here. Next comes Inflow, and this input dialog looks different depending on what you chose back on the initial general input window. For example, this is reservoir well data. You can see the items that you need here: reservoir pressure, net thickness, drainage, wellbore radius, perm, skin, and water cut. And I thought that was 50%, but we'll do that. All right, so let me back up now and show you difference here. So we've got Vogel with reservoir data. That's why that particular one showed up. So if I select one production test, and now I go next, 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 here is my new Inflow input dialog. So just reservoir pressure, water cut, flow rate, and flowing bottom hole pressure. You can add the bubble point if you know it. If not, it's going to calculate the bubble point using one of those correlations from the PVT properties. And you can also, by the time when you're filling out all your inputs, by the time you get to this Inflow, you now have all the information needed to actually for SNP to calculate a flowing bottom hole pressure for you, for a liquid rate, and using the tubular description that you've given it in the wellbore and all the PVT properties. So you simply just push that big button there and it'll calculate a new flowing bottom hole pressure for you. So let's go back, because this data set's built on Vogel with reservoir data, so I'm going to leave it that way. And we'll come back here to our Inflow. Some of the knobs you can turn to cause your IPR curve to tilt one way or another is the permeability and the net thickness. Those are the two big knobs. Wellbore radius and drainage radius are cause less change in the curvature. So next is, since we don't have any artificial lift yet in this data set, it skips over the artificial lift section and comes to sensitivities. So here are the sensitivities that are available for this data file right now because of choices that I've made previously. So I can run a sensitivity on surface pressure, casing ID, tubing ID, and those kind of things. There's some that are specific to the reservoir that you can sensitize against, and then a few items that are affect both the hydraulics and the IPR stuff. But basically, we're going, you'll end up using these most of the time. It's simply just a matter of choosing which sensitivity you want, and then you can enter the data. You can run 19 items in addition to the base case. The base case will always show up here, and then you can put 19 items across here, which makes the output graphs pretty busy. You can choose to type them in manually, or you can fill them by adding minimum and maximum and then telling it how many line items you want, and just fill linear. So you can do that, and it'll populate that over 10 items. When a log series fill, you can do that as well, but I find generally the linear fill is more useful. All right, so I'm going to clear that for right now and go next. All right, so here's match data. So this is rate and bottom hole pressure. So if I want to display this data on my graph, or any of the graphs that would have both rate and pressure on them, for like our nodal plot, for example. And if you look right here, you see a little plus mark. Well, that's the data we have right here, right? 1,000 barrels a day. Oh, that 1080. Sorry, I can't read my screen. 1080 barrels per day with a 900 psi flowing bottom hole pressure. And if I enter that data in here and make a calculation run, that data point shows up here. So the point of this is, if, for example, if I have a flowing pressure gauge in my well, then I can use that data to determine what this rate is, and then I can use that data point to help me tune my IPR curve. Now, when you do that, typically the bottom hole pressure gauges are not located at the perf depth or at the heel of the well, so you will have to make some pressure correlation for the TVD depth between where the gauge is actually at and the inflow point for your well. The other tab here that we use a lot is pressure survey. So we can input the data from our flowing pressure and temperature survey and use that to help us determine what's the best hydraulic model for our wells. This tab here is retrieve from a database. So if you've got us linked to your database, you can simply come in and pick a well name off your list, and it will bring all of those different columns of data in that you can then display or use. So next brings you back to the beginning again. So that's kind of, this is a simple case, not a lot of information in here, no artificial lift. That's kind of how you navigate your way around through SNAP. And again, it's just calculate. So let me talk about this just a little bit. This is this base output report or standard output report. So it gives you the intersections of your IPR and your outflow curve. And oh, here's some manipulation things. All our graphs are, you can control the line shapes and the symbol sizes and colors, line colors and symbols by right-clicking anywhere in the graph. It brings up this chart styles or chart properties box, and the one that controls, the tab that controls this is chart styles. So if I select that, and you notice this group list here, well, that's the same as the index on my graph. So if I like this data point here, it's kind of hard to see, it's a little small. If that's item 3 on here, so if I pick the third item here, then the symbol style, I can say, okay, well, I don't want a cross there. I want a big dot, and I want that dot to be bigger, and just change it to that in there, so that dot shows up there now. The thing about this, though, is that while I have that on here, I can use it to bold a line or something like that, as well as show an individual item. But once I close this and reopen it, it goes back to what it wants to display those items as. So when you make any changes to the style of the graph, you should probably keep a copy of it. And to do that, and the way you make copies of the graph is a keyboard copy, you simply make the graph the active window, do a keyboard copy, and then now this graph is available to put anywhere inside a spreadsheet, for example, inside an email, or anything like that. I'm not going to save that. So it's real handy for doing presentations and stuff. When you've done an analysis, you want to show some of the graphics and output reports. So you can easily copy any of the graphs like that. The other thing about graphs is the scales on the graph. You double click on the X or Y axes, and you can manipulate the chart X or Y axis. There is an automated way to do this, undocumented feature, by the way. If you hold the Shift key down, float your cursor along the axis you wish to change. I'm holding my Shift key down right now. I'm going to double click here. Resizes the graph along that axis to show all the information that's there and maybe not showing because of the size of the graph or the scale that you have here. And it works in both axes. So sometimes when you run a graph and the whole thing's not showing, Snap tries to make the intersection visible in the graph. I mean, it's the most important point. That's what you're looking at, right? That's what you want to know. So the other thing you can do with graphs is you can zoom in on them. And up here is a little magnifying glass with a plus mark on it. So if you select that, now we've got a little rectangle here. I can select an area on the graph and magnify that, zoom in, and then to go back to normal, it goes back this way. Yeah, and this other one, I'll show you this when we look at a sensitivity that will show total production, and you can flip the graph from total production rate to oil production. So that's useful in some cases. All right, let's see. We did this. You get to there and there. There's a little bit about graphs. Output reports. Snap does a lot of stuff in the background. Doesn't always show you all the reports that are available, but they're all available up here. Okay. So all the report windows are all text boxes. So you can copy that, and like we did before, paste it into any other Word document, Excel file, however you want to manipulate that data later. It will also export to an Excel CSV file. There are usually multiple pages on these reports, and you can scroll through those to see. So here are all my inputs, for example, and then some of the output values here. This is the inputs for the Vogel reservoir stuff. And then here's some of the outputs that it calculated. And here's my well data. My flow diameters, depths, vertical depths, angles, segment temperatures, pipe roughness, and wellbore correlation that was used. So all that information is in this standard output report. So here's another one. I don't know if there's any data. Yeah, there's no data in this one yet. There's an output report that shows all of the myriad of calculations that Snap does. So right now it's not showing anything, right? Yeah, okay. So to make that visible, and it does take a little processing power to do that. So if I go to my general input and back to this additional hydraulics rates tab, optional input over here, this big cell right here is where I tell it to put a file name there. A simple character will work, but if I just give it a name and then recalculate everything, and now under reports, hydraulic reports are available. Oh my goodness, look what we have here. So we've got, and there's a whole big list of stuff, right? So there's a page of information for every flow rate that was investigated. And the first, in a lot of the graphics and a lot of the reports, the first page is going to be the solution rate. That's what this is here, approximate solution rate details. So here's all your pressures at each 200-foot segment, oil quantities, your total GORs, GLRs, lift gas if you had any, viscosities, and on and on and on. Here's your liquid hold-up fractions, all this kind of stuff. So, and again, there's a page of data for every different flow rate. See, we're up to 50 barrels a day here. Next page is 70, 100, 141, on and on and on and on and on. Okay? Again, this is a text report. You can copy any of that information out of there and put it in what other app you would like to use that data for. So that's pretty much how to navigate through a basic SNAP data file. We haven't talked about other than a simple sensitivity. It's as quick and easy as this. So just put that sensitivity in there and recalculate. And here on my nodal plot, you see different flowing flowing wellhead pressures that it analyzed. Here's another thing about graphs. If I select the line item in the index, it'll bold that line, and sometimes you can get some really busy plots in Snap. So if I just hold my left button down, drag my cursor all the way out of the graph, that line stays bold. So again, if you're trying to do a presentation or something, you can bold the line that you're interested in, copy the graph, make it, it's the active window, of course, copy the graph, and that line will show up on your, you can paste it into your email or PowerPoint presentation. If I click outside the graph or back inside the graph, then my bold selection goes away. All right, quick and dirty, right? So that's navigation, looking at most of the input dialogues. And again, be aware that depending on what you choose here and here and here and here, then some of the inputs may be different. And certainly some of the, well, let me show you this one other one. So if I select detailed gas lift, for example, let me just show you basic gas lift. When I get there, it's just going to want to know a few basic items. What's the specific gravity of my lift gas? That could be different than what my produced gas gravity is. So Snap will mingle those nicely at the injection point. This says, where do you want to inject your lift gas? 5,000 feet in this case. What's the operating pressure? Do you want a TGLR, or you want to talk about injection gas rate? So here's 1,000,000 cubic feet, injection gas rate, and for my data set here, it says, oh, that'll be about that much. So if I apply that, there's my, let me close this dialog so I can see behind. So here's my quick basic gas lift output. Move these guys around out of the way. So here's my gas injection pressure at 5,000 feet. It's my flowing gradient showing the inflection point right here where I'm injecting gas. So this is with lift gas and formation gas both. Below the injection point, of course, this is formation gas only. So that's what that would look like if you selected just basic gas lift. If you select detailed gas lift, when you get there, oh my goodness, I have to put in all of this stuff, right? But it's basically, it's common stuff that you're going to see every day with gas lift, and we're going to do an example a little later and show you how this all works. But here you'd have all the valve details, depths and valve types and valve ODs, model numbers, port sizes, AP-AB ratios, and all that kind of stuff. So, and then there's a troubleshooting routine here as well, which we'll also look at later on. I can add additional hydraulic rates to my gas lift graph if I wish to by looking at that. So it's just an example of how things change when you make selections along the way. It's been 55 minutes. I'm going to try to take a 5 or 10 minute break every hour. So right now it is 5 minutes to 9 o'clock here in Denver. So I'm going to take a quick 5-minute break. I'll come right back at exactly 9 o'clock and start up again. And we'll look at some other nodal analysis stuff that Snap can do. All right, so let me pause this for a moment and we'll come back to you. Okay, everybody. This next section is going to be a preview of what nodal analysis is, and then I'm going to show you in Snap what we can do there. So to get started, let's see. Here's what we're talking about. Nodal analysis, we're looking at the whole flow system from our reservoir up our tubing pipe through the wellhead to our separation facilities and finally into a storage tank or a flow line. Excuse me. Sorry. That's going to continue probably. But anyway, so this kind of little schematic shows you what we're talking about. We're going to flow through the reservoir into the wellbore, up whatever tubing we have, through our wellhead, through our test separator, and separate out and down the flow line. So really what we're talking about is predicting and forecasting production rates, deliverability capabilities for our wells. So we need to have a good understanding of both the production system, all the mechanics below ground, above ground, stuff like that, as well as our reservoir fluids. So nodal analysis result or thing will include reservoir, both IPR responses, wellbore, the completion, the tubing, and all that stuff. Everything from the heel of the well, the perforations, all the way up to the tank battery. We can do it simply, or we can add artificial lift and stuff like that. So here are the different PVT properties that we commonly use that we need to know. Formation volume factor, produced oil gravity, GOR, solution gas, compressibility, bubble points, and that's probably not all, but just a small list. So what then we're also analyzing the reservoir through the IPR, inflow performance relationship. So that's basically what drives fluids from the reservoir into the wellbore. So what we're going to do, we're going to take that pressure drop plus all the pressure drops throughout the whole system until we get to the surface or whatever particular pressure node we select within the system or at the surface. So here's basic IPR information, right? You want to know the delta P from the flowing wellhead pressure to the separator. That gives us the energy and stuff that we need to get our fluids to the surface. So what we do is we separate the system into two segments. The reservoir segment, which is the inflow performance relationship, and then the piping system, which we'll call outflow. Some people call that vertical lift performance, but there are a couple of different names for it. But with the goal of analyzing this as a system. Here are all the things that we need to know, or that we're going to try to figure out, I guess I should say. So starting at the bottom of the well, fluids flowing through the reservoir rock into the bottom of the well, and then all the pressure losses up the well. Add all that up together and you end up with what that value is, total pressure loss. And unfortunately, just one part of the system can cause some severe restrictions. You can have a pinched pipe. You can have a wellhead choke. That's probably one of the most common things I see is somebody put a wellhead choke on and forgot to open it or only opened it partially. Sorry. So we're going to consider the whole production system a single unit. So, and that's called nodal analysis, right? We pick a particular node, but we're actually trying to analyze the entire system. We can estimate flow rates. We can help select tubing sizes, flow line sizes, what's wellhead pressure, surface choke sizing, or since I'm a gas lift guy by nature, I don't like chokes. It just backs up our production, right? So anyway, estimation of what our reservoir effects can be and identifying different flow restrictions in our systems. We can use nodal analysis to size subsurface safety valves, evaluate perforation density, gravel packs, artificial lift designs. In SNAP, we do both gas lift and jet pumping. We don't do ESPs, although we can use the ESP information to create our inflow IPR information and then move forward to designing a gas lift or jet pump installation using that inflow performance relationship. We can evaluate all kind of wellhead pressures, gas injection rates, angles of tubing, and all kind of stuff like that. So the reason it's called nodal analysis is that we pick a particular point in the system, figure out all the flow coming into that point and then flowing out of that point. So we break it up basically into those two items, inflow and outflow. Typically the node we're going to pick is going to be the mid-perf depth or the heel of the well. That's going to be our known node. That's where we're going to want to calculate our solution point for our nodal graph. So here's, kind of things we need for, yeah, my tang's all tangled. Anyway, so inflow and outflow, right? So inflow is just the stuff from the reservoir. That's your reservoir pressure minus the DP through the reservoir to the node, mid-perf depth or heel of the well for a horizontal. Then outflow is everything else. It's the tubing IDs where the fluids are going to flow to the surface. It's the deviation of the wellbore. It's the roughness of the pipe. It's the wellhead size. And is there a choke body? Is the choke pinched back? How many elbows are in the flow line? And what size is the flow line? All those different things, but it's basically two, inflow and outflow. We're going to pick that point, and that intersect, you can pick other points, but typically we either pick, the surface wellhead pressure or the flowing bottom hole pressure in the well is typically the most one used. So here's what a typical nodal analysis plot or curve or graph looks like. The black line here is the inflow performance relationship curve, the IPR curve. The red line is the outflow curve, VLP curve, as some people call it, or as one of my mentors, Dr. Kermit Brown, from long ago, he called this tubing intake pressure. It's the pressure required at the bottom of the tubing to push this liquid rate to the surface. And in common nodal analysis terminology, we simply call this the outflow curve. And here's another example, IPR curve. So this one was just a single tubing size in it, or just casing flow perhaps, and then a sensitivity to diameter tubing. What you'll notice is as the tubing diameter increases, the flow rate prediction, the intersection, will typically increase as well. The curve will move downward to predict a higher flow rate. Anywhere in the system, yeah, okay. So let's look at SNAP, or, well, let's see if I can get there. There it is. Okay. So here's the data set, and I'll bring it over here so you can see it. And here's the data set we're going to work with right here. It is SNAP Nodal Analysis.snp. And you might have that from your from the list that Jessica provided for you. So we're going to demonstrate some of the different things we can do with nodal analysis. Again, here's the general input dialog. It's going to be an oil well, relatively low pressure and temperature. And here's our PVT properties, 1001 GLR, etc. It's our wellbore. And again, in SNAP, the last line item in our wellbore description is going to be where our downhole, our flowing bottom hole pressure calculation is being generated. Do have wellbore geometry. I do have deviation survey in this one. Let me show you another thing about this particular one. If I do have a deviation survey, it makes it a lot easier to come in here and describe my wellbore. So with the deviation survey in place, all I have to do is put 1,000, 2,000, 3,000, etc. and to describe the wellbore. If you look right here, there's a plot trajectory button, and that brings up I'll move this out of the way so we can see that. So this one is set up just as kind of a straight angle. And you see Snap is calculating the angles here from these input values. And what you get is this is the well's trajectory. And it's overlaid over the deviation survey. All right, so next, and then here's the inflow information. Vogel 1 rate test was the inflow model selected. So it's our reservoir pressure, water cut, flow rate, flowing bottom hole pressure, and no sensitivity selected yet. This is basically that same one. So if I wanted to do some sensitivities, I would simply open, and again, what I did just now is once you've used this for a while, this gets covered up by a lot of your output windows. So you'll eventually learn to use probably these toolbar items here. And so this one right here is the sensitivity one. So for surface pressure, and I think we showed this one a while ago, but we can do one for tubing ID since this is a flowing up tubing well. So for what happens when I do this, and then I'm going to have so this is the same item list or the same line items as on my Wellbore description. So if I want to do a different tubing size, I need to add all those in here. So I'm going to try this, demonstrate this. If I grab that, right click, and it will fill down. So that's not, and then I have to make it the same as, end of tubing as before. I'm going to do that. So I'm just going to show 2 for this, but so you just populate your grid with the same number of line items and stuff that you had initially. Here's the base case, right? And then sensitivity 1, I've got set at the same numbers. And we do that purposely because the base case, when you draw the graph, the base case simply gets labeled as base case, and it doesn't necessarily tell you what the size of the sensitivity is. But when I put the values in here, I'll have in the legend of the graph, I'll have, this size tubing and this size tubing for the two. So, okay, so if I say okay and calculate all, then my nodal graph shows both tubing sizes. Again here, so there's my IPR curve, hydraulic, and here's hydraulics base, but that's the same as 2.441 or 2 7/8 tubing sensitivity case. And there's the 2 7/8, 3.5 tubing. Sorry, my throat's a little messed up. What you'll notice, and here's that shift double click thing again. When you look at your outflow curves, a stable well will have a positive sloping outflow curve, certainly at the intersection. So at this area where we're interested in, if our outflow curve is positive, sloping, then that's an indication that the well is going to be more stable. As you can see at these lower flow rates, over here, everything starts getting very unstable. They start, as a friend of mine says, they get unhappy. They're not happy over here. So for low flow rates, you're going to end up, this indication of a negative slope on my outflow curve will indicate that the well is going to be very unstable. So that's one of the things you can do in this simple model here. But as we go forward and looking at artificial lift and looking at gas lift, there are many other sensitivities that we'll look at along the way. So let's see. Let's go back to my presentation. I think that was okay. That was the end of that. All right. Let me start the next one. And so we're going to jump to jet pump design and start here. This is going to probably be pretty quick thing here. Jet pump design and Snap is relatively simple. So here's kind of quick intro to jet pumps. You're not familiar with them. Jet pump is an artificial lift method that uses a power fluid through a small jet into a converging diverging nozzle, which creates a low pressure at the point where the nozzle is just above, the ejection port nozzle is just above the throat of the jet pump, and just outside of that area is the low pressure area. That's the suction of the jet pump. You can use either water as the power fluid or dead oil, any compressible fluid. Gases don't work very well for jet pumps. A jet pump is a mass to energy conversion device. So you have to have a power fluid with mass to make the jet pump work well. So if you want more information about this, then everything in SNAP jet pump is from the Petroleum Engineering Handbook or from this Hal Petrie's book on jet pumping wells. So here's the SNAP data set for that. I'll bring it up and you can see which one it is. So you can open the one we're using here, and the file name is jetpump.snp, just simply that. So with this one, I've got this data file set up specifically for jet pumping. All the initial inputs and stuff are the same as we've looked at already. So I'll just blow through these rather quickly. So a little bit different than before, but still this is just, normal information that you would have. Here's your one rate. So we're looking for 1,000 barrels a day at that kind of flow rate, flowing bottom hole pressure. Sorry. So here is the input for jet pump. Let me go back to the general input dialog. This one right here. So what we've chosen here is, on the general input dialog, we've chosen jet pump. So now when we get to what would be our artificial lift input dialog, it shows us the one specifically for jet pumping. So when you look at this, is all the input information and stuff that we need to size a jet pump for a particular flow rate. So here's pump parameters. This I'm having trouble with my tongue today. Here's the drop down for different manufacturers, and we have a whole slew of them, right? Kobe, Oilmaster are old jet pump manufacturer types. Both of these are owned by Weatherford now. Giberson is also an older one. Several of the jet pump manufacturers use the Giberson details to manufacture their pumps. Of course, there's TechFlow is one of the newer companies involved in the business. I think that's a Tally company now. So each one of these manufacturers or service companies have different ways to describe their jet pumps, their nozzle and throat combinations. But basically it's a grid of nozzle sizes and throat sizes that you can mix together for different results. For the Oilmaster one, it has a index list of nozzle sizes, and these nozzle sizes relate to some specific ID, but in their nomenclature, in their system, it's just an index number for the nozzle and a letter index nozzle index for the throat size. But again, that throat size corresponds to a particular area, and we actually have those areas of diameter shown here. So as I change my selection here, it changes what the diameters are going to be using. And within SNAP, we can, we have to account for different things, different models and stuff. So even if you have a new manufacturer vendor and we don't have their specifics in our list here, you can set the arbitrary sizes here, and you can edit these areas and diameters for the specific pump that you are installing. Otherwise, you can use the background stuff that's already in the program. Water or oil selection for our power fluid. Of course, that's a density thing, right? It's going to help us calculate what power fluid pressure is at the pump depth. And then, much like an ESP, jet pumps displays work on what do you call it? Pump curves. So, and here's the pressures that we're going to investigate, from a minimum of 1500 to a maximum of 4500, and it'll do this in 4 steps. So I picked values here that evenly increment from this value to 4500 in 1000 psi steps. You can specify the power fluid density in either API oil gravity or specific gravity. Right, over here on the right side, what direction we're going to put the pump in. Typically, we're going to do reverse flow, which is where we put the power fluid down the tubing, down the annulus, and bring combination of power fluid and produced fluids back up the tubing. Now, you can switch that to these other cases. You can do, parallel strings, or you can put the power fluid down the annulus or down the tubing and bring the production up the annulus. So we have to know what is the production tubing OD, because we need to know things about what this annulus is, and the casing ID, the pump depth, and then the perf depth. No, that's not going to work because my pump depth is above so let's put that at 8,500 feet. And we can choose to model this with the gas vented or not. Typically gas is not vented in my experience. And then down here is what flow rate do we want this pump designed for. Okay, so we've gone through all these already. PVT, IPR, tubing, gas. So if you want to go back and review any of these things here, you can go quickly back to here, or you can go previous in this input dialog. All right, so one thing I have not talked about a lot is this button right up here that says Save My Inputs. So I'm going to do that right now. And it's especially important when you're, now this is, a real simple model, but if you're fleshing out a very detailed wellbore geometry, or you have a lot of gas lift valves or anything like that, when you get to where you're going to run your case, we try to trap typing errors and stuff like that, but it's not 100% foolproof. So sometimes Snap will crash on you if you put 2 decimal points or something, but we try to, like I said, we try to trap typos and stuff like that. But anyway, so we've got all the input information in here. We've got our pump manufacturer model type picked. We've got our nozzle and port size selected. And so we're just going to say apply right here. And I'll turn this off so we can see the output. So again, we get standard report just like before with all our input stuff in it. So I'm going to just turn that off right now. And here's my jet pump plot curves at the different power fluid injection pressures, surface power fluid injection pressures. It's my IPR curve. And here's the legend, tells you which ones are which, right? And here, this blue dot right there, that is my desired requested flow rate. So, and over here on the output, here's where it tells me I selected, requested 1,250 barrels a day. That's going to, with the IPR curve that I have, then that's going to require a flow mud hole pressure, 2,347 psi. And here's the breakup of oil, water, and gas that will be produced. And here's the specifics for this production, for this solution rate here. So here's the power fluid injection pressure at the surface, and here's our power fluid rate. Here's our intake, equivalent of the flowing bottom hole pressure, but at the pump depth. And then here's our pump discharge pressure, and here's the power fluid pressure at depth. So 4,816 psi. Surface generates at 8299 psi pressure at the pump depth, and the fluid horsepower required is calculated to be 202 horsepower. All right, so if we put that 9A jet pump in this well at those depths with these PVT properties and tubing IDs, OD, casing ODs, and stuff like that, that's what we're going to get. We'll get this result show up on the graph like this. If the other thing is, if I use lower power fluid pressures, you can see on the graph what other rates I might be capable of simply by reducing the power fluid rate and pressure. And then down here on the output report is individual curve rates, the intersection rates. So 675 barrels a day, if you're only lifting it with this much power fluid pressure and rate, all the way up to the 1200 rate up here. So I selected, in this one I happened to select a power fluid rate just greater than the pump curves I told it to use. So if I come back here and go back into my, this is the artificial lift icon here. So I can say, well, what if, okay, I don't really want 1200, say I want 1050. So I'll request that amount. It says, okay, well, the bottom hole pressure would have to be that because the IPR curve, when I do apply, then it's going to reset everything. There's my requested flow rate. And now my solution information says, well, I only need 3,550 PSI for this and a fluid horsepower requirement of 130 PSI instead of 202 that I had before. So for doing this, it's kind of iterative, I guess. You just put all your PVT information, your IPR information, all that has to go in here because everything is based on this IPR, right? We have to honor that, and what our well is going to produce is going to be where our pump curve intersects our IPR curve. Same thing for any nodal analysis plot. It's the intersection where all of our stuff agrees. All right, so that's pretty simple. Well, it's not simple. It's jet pumps are quite complex in the ornery, but that's how you would do a jet pump calculation. And then, doing troubleshooting, what you would do is you would look at your actuals. So I'm going to go say, okay, my trend says I've got 3,000 PSI and a flow rate of 1,500 barrels a day. What is, so if my jet pump's doing that, if it's not matching up with this very well, then that's an indication that either your nozzle or your throat have some erosion damage, and they're not the precise sizes that they were intended to be. So different people use different methodologies for powering these jet pumps. Some people will use a big hydraulic pump at the surface. I worked in an oil field called Kaparic on the North Slope of Alaska for many years, and we had I had 25 or 30 jet pump installations in the field, and we used our produced fluids reinjection water lines. So we had a big water flood going. We used our produced fluid to power the water flood, and so we had high pressure water at every drill site. So that was our power fluid. There was another field up there that I'm familiar with called Melody Point. It's a hill carp operation now, and they use fluid pumps at the surface to provide their power fluid volume and pressure. So different ways to do it. We're going to move on then. Let me ask right now. Anybody have any questions? You will pop up there in the chat, and I'll see if I can answer them quickly, and then we'll move on. Oh, hi, Omar. Related jet pump design we may have to consider is the corrosion rate in the tubing, mainly when we design reverse mode and try to maximize production in new installation. We usually end up to reduce the rate, be in range or below standards on corrosion rate, not fully optimized, or without fully optimizing the well rate. Yeah, certainly you have to be concerned with erosion on your tubing, on your tubulars, as well as your jet pump items. So that has to be taken into consideration with your design and operational methodology. Okay, all right. Then we're going to move on. One of the items on our to-do list here today is to demonstrate flowing gradients and to being able to calculate flowing bottom hole pressures. So I'll do that now by using one of the other files that we have available here, and I think there's one called Snap BHP Calculator or Calculations. So let me start that one up and then bring it over here to my display window. So this again is a simple, relatively simple Snap data set, and it's set up right now for surface pressure calculations. Since I have those surface pressures as a sensitivity, when I run this case, it will show me a nodal plot with those surface pressures on there, right? So, but what it does at the same time is it does generate a flowing pressure gradient. So under graphs, if I look at flowing pressure gradients, the first, and this works for all, or this system is the same for all of these graphs. The first item in the drop down for any of the graphics is always going to be the solution rate. So if I pick that top one in the list, it's going to show me the solution rate for whichever one of this 1,000 barrels a day, okay? So this flowing gradient is the calculated values every 200 feet roughly for this flowing well. So it's no sensitivities on here. So if I would like to see 1,000 barrels a day flowing gradient graph or gradient, then I need to pick another item in the list. So look at my pressure gradients. It's actually calculated flowing gradients for every one of these flow rates. So the solution rate will only show you the base case, but will also have calculated, or if you put, and here's, I guess I should say this, all along here, here's how our outflow curves are calculated. Shift double click. Snap takes the Qmax value from the IPR curve and calculates a flowing bottom hole pressure, intake pressure, outflow pressure for that flow rate and plots it on the graph. Then it takes 50% of that flow rate and does the same thing, calculates that value, 25%, 10, 5, and so on. And you can add additional rates in there. We're really interested in this intersection here. So what Snap is doing is it's just drawing a straight line between any two adjacent outflow points, calculated pressure points. To add additional outflow points to this to maybe make sure that this is a straight line going through my IPR curve, in your general input dialog, there's a tab that says additional hydraulic rates. And so if I put a value in here, here is 900. So let me put 900 in here, and you can put in a total of 10 items in here. So now when I recalculate, I get a new data point here at 900 barrels a day. So what this allows me to do is maybe put a calculated point on either side of my intersection to assure myself that my line that's being drawn between any 2 points is indeed correct. All right, so graphs, flowing pressure gradients, and I can get any of these other rates with all the sensitivities. So here's 100 barrels a day at the 3 different sensitivities. The other thing, so we can generate can't speak. We can generate flowing gradients for any flow rate tubing size configuration. You simply build your data set with proper wellbore description that you're flowing up, and it will calculate flowing bottom hole pressures for any of those and allow you to draw a graph. And of course, there's also a gradient report for each one of those flow rates as shown here. So there's the solution rate, first one in the list, right? First page in the list here. So, and then it goes through all of the other production rates. So there's your total liquid rate there. That's all the different ones it's investigated. So again, here's 1,000, right? So here's all my pressures, fraction liquid fractions, transit time. This is transit time from whatever depth to surface. From bottom of the well to top of the well takes 22 minutes for a drop of liquid to make that transition. All right, so we can do the same thing with other sensitivities. If I just clear these and say, okay, I want to do one for tubing size, then I think we looked at one of these a while ago. You know how to do that now. This model, you can also do constant reservoir, or you can do reservoir pressure. And I'll show you this one right now, but this is not what, a pretty good job. All right, so I picked two different reservoir pressures. So what you can see is that, and this is a thing for unconventional wells. We know unconventional wells, the effective reservoir pressure declines over time. So you can actually investigate that decline in production rate by investigating or run sensitivities through different reservoir pressures. And what you'll see happening is that flow rate's going to march along your outflow curve. So I would have in this case, a graph for 1,000 barrels a day with my two sensitivities. Why is it? Oh, it's just one line item. Okay. So let me show you. I'm going to show you one. So everybody happy with that, I hope. I've got another example here. If you pick this one, I think, declining reservoir pressure. Well, come on, run. There it is. Run. Okay. Let me make sure this is the one I wanted. Nope, not the one. Okay, it's the other one. Okay, I'll be right back with you in a minute. Let's see. Yeah, okay. So this example is actually a real well out in the Delaware Basin in far west Texas. And on this nodal plot, you can see in what we've done here. This a gas lifted well, and we've run the analysis on this. Here's the sensitivity, and we did sensitivity to reservoir pressure. Okay, so what we've done here is we've used the IPR type for reservoir data, right? And I tuned the IPR based on this for a current data point. So what you're seeing here is the nodal plot showing all these matched data values. So this particular well has a bottom hole pressure gauge in it. And those data points here are shown up on the graph here. And these are the flowing bottom hole pressures from that gauge over time when the well was relatively young and how it's progressed over the last 4 or 5 years of its life. So when you look at this, you can get an idea what's going to happen to my production rate and consequently what's and why. And it's because the reservoir pressure is actually declining over time. And so if you put more, you can see the intersections. They follow the outflow curve pretty well. So following the outflow curve, we can see over time. Now, there's no way to predict when in time these reservoir pressures are going to be valid, but gives you the idea, okay, here's what's going to be happening as time marches on. So I find this a very, very interesting analysis. All right, gradient curves, flowing bottom hole pressures, that's all. I think we've done most of that, I believe. Okay, so let's move on. We're almost at the end of our second hour. I'm going to go to another presentation showing how SNAP does gas lift. Oh, that's the jet pump one. Oh, okay. Just says, what? That's odd. Okay. Anyway, I think I got some slides messed up. Here's a continuous flow gas lift well. The schematic there, the little cartoon shows gas being injected at the third valve down from the top. And equivalent graph here is our gas injection pressure in the annulus and our flowing tubing pressure gradient. So we've got a differential between the flowing tubing pressure at the valve depth and the gas injection pressure there. So I can inject gas in the well and reduce the density above that point. And that's what gas lift is all about, is density reduction. So if I'm able to operate at a deeper depth, then you can see that my gradient changes and I'm aerating a longer length of my wellbore and generating a better drawdown, increasing the flow rate out of the well. So that's what gas lift is all about, is reducing the density of the flowing fluids in my well. It's a supplement to your reservoir gas, and we're increasing the gas liquid ratio at that injection point through a gas lift valve or an orifice valve. I'm not going to talk about valve mechanics today or different types of gas lift valves, but certainly could be available to do that for any of you if you wish in the future. So the other thing that happens when I add lift gas is I increase the mixture velocity and I change the vapor liquid distribution or flow pattern to one with better mixing and reduced liquid holdup. Liquid holdup is defined as the volume of liquid and gas in any section of my tubing. So if you take a 1 foot section in the tubing in the well and calculate the liquid and gas in that, the amount of liquid and the amount of gas, that percentage of liquid in there is the liquid holdup. So of course the objective of doing this artificial lift method of gas lift is to reduce the flowing bottom hole pressure. So here's what happens. Then this is a this is called a gas lift performance curve, gas injection rate versus production rate. And we'll show one of these when we do the example of how to build a gas lift design. But what you see here is little or no lift gas. Oh, sorry, this one's versus depth. Okay. So the same thing would work with injection gas. So at high depths, you're not going to get much rate. If you move your injection depth deeper and deeper in the well, you get to a point of diminishing returns, you start plateauing off, and this really classically looks like more of a gas injection. Yeah, it's labeled gas. Oh, it's labeled depth, but it's actually rate. I didn't notice that before. All right. So this is really gas injection rate versus liquid production rate. So at low gas injection rates, you get no flow rate out of this particular well. As you increase your injection gas, you get increasing production rate up to a point. All right. And you'll notice here that after this point here on this graph, well, production rate starts to decline as my lift gas rate continues to increase. So, you know, field operations folks say, oh, well, little lift gas is good. More lift gas is probably better. Well, not necessarily. If you add more and more lift gas, what you're doing is you're increasing the total volume of fluids that you're flowing up the tubing. And eventually, that increasing fluid volume increases the velocity. And as the velocity increases, the friction on the pipe walls increase. And the result is that the flowing bottom hole pressure you're creating is actually rising rather than declining, which is the goal that we're looking for. So again, it's labeled wrong on the graph, but it's showing if you move your lift depth up, down, then you get more rate. Okay, kind of common sense. Okay, and because, you know, as we demonstrated there, best lift occurs when the injection is set at the deepest point possible in the well. That's not always the bottom gas lift mandrel depth, but you do get more drawdown. It requires less lift gas to generate the same flow rate, and it helps improve or mitigate slug potential in horizontal wells when you can lift deep. We can increase production rate from naturally flowing wells. We can produce wells that would not flow naturally. We can dewater gas wells. In fact, the San Juan Basin is famous for doing this. The coal bed methane there are thousands of wells there that are on gas lift, keeping those shallow, very low pressure reservoir pressure wells flowing. And you can use it to backflow water injection wells, of course, to maybe clean up your perfs or something like that over time that tend to get clogged up over time. But here's what we have to do gas lift, is we have to install some downhole equipment. Gas lift valves mounted onto mandrels, and both conventional mandrels where the gas lift valve is mounted onto the outside of a pup joint, or side pocket mandrels may be used. So this spacing allows us to move the injection depth to a deeper point in the well. You've got to space these valves properly given the resources that you have and the flow rate that the well is going to generate. And by resources, I mean the gas injection pressure and rate available at the wellhead. We also have to set our pressures on our unloading gas lift valves properly. So that's based on the injection pressure, the valve depth, the valve type and size, and port size. And what we're doing with those valve pressure settings is that we are allowing upper valves to close as we move our injection point deeper and deeper in the well. Initially, when we install a gas lift installation, those valves are set up to operate with a gas injection pressure on the casing side and a flowing fluid pressure on the tubing side. When we initially complete a well with gas lift equipment downhole, we've got typically tubing full of fluid and the annulus full of fluid. So all of our gas lift valves are open. So our job is really to close those upper valves as we unload the well and operate the well. So I'm at an hour here. Take a quick break. I need to rinse my throat a little bit, so my voice is getting a little hoarse. I'm going to have a little beverage here, Diet Pepsi, by the way. If you're good, let's see, I'm at 9:58 right now. Now come back in 5 minutes, please. Welcome back, everybody. It's 10:03 here in Denver. For the next hour, finish up this presentation, I'm going to talk about spacing gas lift mandrels using the SNAP app. So here's a brief introduction to how that process works or what we have to do. So then we'll jump into doing what we're going to show some in the presentation here, and then we'll get into SNAP and show you how it works in SNAP. So here's what we have to do to build a gas lift design. We have to set injection points in the well. Gas lift valves on side pocket mandrels or inside pocket mandrels or on conventional mandrels. So this is how you set the depth of the top valve. This is my wellhead pressure, and this gradient right here is my kill fluid or completion fluid, the gradient of that fluid that's been left in the well, filling both the tubing and annulus typically. And then this line is my gas injection pressure, my design gas injection pressure. So with my kill fluid gradient, my gas injection pressure gradient, gas has a little density too, so it has an increasing pressure as we move downhole. So at this interception point here, that indicates the pressures are equal at that point. So I cannot inject gas there, so I have to place my first mandrel uphole approximately 100 feet. So depending on what this pressure gradient is, in this case, look over here, it's 0.465 psi per foot, and you'll see that a lot of gas lift vendors using that 0.465, 0.45, but what you should actually use is what is the actual kill fluid gradient that's in the well. Just as an FYI, interesting little factoid, the Gulf of Mexico seawater happens to be 0.465 psi per foot, and that's why you see it in a lot of gas lift designs from many of our vendor communities, because that's where we started doing a lot of gas lift in the U.S. is in the Gulf of, near shore Gulf of Mexico, and Gulf of Mexico seawater was used as the kill fluid. But anyway, so I have to move that mandrel up from the interception point here about roughly 100 feet. And so that gives me a 46.5 psi differential to start injecting lift gas at this depth. All right, so here's the grid in SNAP that shows putting that valve at that depth, port size and everything, right? So when I push apply on here, I'm going to get the next display. So here's what it looks like in SNAP. I've actually typed in this case, starting manually doing this, typed in that value, done the math, right? And done that. And then, so now I've got the first valve set in my well. So to get to the next valve, space my second valve, I have to pick this. I've got this valve set in here, and I have to pick what we call a transfer pressure. So this is some pressure that exists in the tubing at the depth of the top valve. So if I pick a pressure here to use, so what I'm going to do is I'm going to parallel kill fluid gradient line, my unloading gradient. I'm going to parallel that down here, and I'm going to pick some point to the right of my objective liquid gradient. So if I pick a point over here, then this valve is going to, the next valve downhole will be relatively shallow. If I pick a point here, then that's probably about the most aggressive I want to be, because this outflow, this fluid gradient curve here is telling me this pressure right here, that's the minimum pressure that's going to exist in this well at that flowing tubing pressure. So if I select my transfer pressure over here, it's going to increase my spacing, but it's going to make it very, very difficult to cause that point to actually exist in the tubing. Transfer pressures are typically chosen at or just to the right of the objective liquid gradient. It's 500 barrels a day in this particular case. So to do that, we pick that point there, construct this same gradient line from that point down to intersect my gas injection pressure. So like this. So now I have two valves in my well, and as I unload fluid from one valve, I'm operating at a gas injection pressure here, and I'm moving my flowing tubing pressure along this depth line. So if I had a gauge here at my gas lift mandrel depth, I would see this pressure moving slowly to the left as I increase my gas injection rate. Till I get to here, when this pressure exists in the tubing, I have this gradient fluid below me in the casing. So this gradient line indicates what depth I would when I uncover the second gas lift valve, or this is the place I would put the second gas lift valve, because that's the deepest I can uncover or reduce the level of kill fluid in my annular space. So I space my second valve there. That information gets translated into SNAP or into the detailed box here. And here's an interesting, this gas lift stuff works. When I'm injecting gas just here, I'm moving my liquid level down in my annulus until I get to this valve. So now I'm injecting gas through two valves, but I'm controlling my gas injection rate at the surface at a rate just greater than the capacity of one of these valves. So now that I've got two valves open, my gas injection pressure is going to naturally decline or decrease. And it's going to decrease until this valve closes. Okay? So now I'm just operating on valve 2, but as indicated here, this green bar says this is the opening pressure on the gas injection pressure side, and this is the closing pressure. So once I get this valve open and now close the top valve, this is all the casing pressure or gas injection pressure I have left to be able to place my next valve. So that's what this stuff says. So here's the math to do all that, right? And then, but really it's a matter of just graphically picking a transfer pressure point here and constructing that gradient line, same kill fluid gradient line, down to the closing pressure, the equivalent gas injection pressure equal to the closing pressure of the top valve. Okay, and then I would take another pressure drop to close the second valve, and then instruct the depth for my fourth valve, and so on and so on, right? Yeah. Why is it doing that? Okay, move my, sorry, do my spacing down. Now, you'll notice here that we get to a point, we've taken some casing pressure drops to close these upper valves, and now we can no longer move our gas injection point deeper, but we always want to go ahead and place mandrels to the end of the tubing or to the packer if there's a packer. If we have no packer in the well, just open-ended tubing, then the tubing tail actually acts as our bottom gas lift injection point. But we would go ahead and space valves at some even spacing number here, some bracket below this point here. So typically we'd call these unloading valves and then operating valves down here in this area. All right, so let's open a SNAP data set where we can demonstrate that in SNAP. So this is mandrel spacing whit.snp is the name of the file if you would like to follow along. So again, similar stuff here, general input dialog. Oh, well, Vogel 1 production test. Now I've selected detailed gas lift. Just preview these first things. This is stuff we've seen before. Reservoir temperatures, reduced gas gravity, formation GUR, API gravity. And then here's my wellbore description. You'll have a deviation survey here. I do. All right, so in this case, this demonstrates the use of the deviation survey to build my wellbore. If I did not have the deviation survey, then I would have to just go in here and select different MDs and TVDs. And the idea here is to roughly set a line item at every 10 degrees of deviation in my wellbore until I get to my tubing tail. And then at the tubing tail, that's a line item for the tubing tail. And then I've got a line item here at the bottom of the well or at the perforation depth. So next, my inflow information. We can now click that button if we needed to set the parameters for our IPR curve. And then the next one is our artificial lift input, gas lift being the choice here. So we're going to use 1,000 PSI for our gas injection pressure, and design wellhead temperature, loading gradient 0.44, injection gas gravity 0.7. That could be different than your produced gas gravity, so pay attention to that. And here's my desired, that's the gas injection rate. Here's my desired liquid production rate. So I'm showing no solution rate right here because this case has not been run yet. So let me do this. And there's my nodal plot. Get rid of that. And there's the first gas lift wells, valves. And then, so when I get back to here now, since I've run the case, I didn't run the case initially, so it did not know any IPR information. But now it knows that with that flowing bottom hole pressure and 600 barrels a day down here generates that flowing bottom hole pressure. So I'm going to use that for my IPR curve. So the next thing is I can focus either on injection gas rate or my total gas to liquid ratio target. I find it easier to use, or preferentially, I like to use injection gas rate because that's typically what I see when I walk out to my well site and I look at my wellhead and I've got a gas injection choke, adjustable choke, and a meter run, and it's showing me what the gas injection rate is. So I typically focus on that. And this selection cell here says, do you want to do a IPO design or a PPO design? Okay, well, what the heck is that? IPO, injection pressure operated valve. PPO is a production pressure operated valve. The vast majority of every gas lift installation in the world is going to be IPO, gas lift valves in there. So the mechanics of that valve have the gas injection pressure acting on the outside of the bellows in the valve and the flowing tubing pressure acting under the port in the trim of the valve. So that's injection pressure operated. Production pressure operated would be changing where those pressures act. The injection gas pressure would act under the trim of the valve, under the ball and seat, and the flowing tubing pressure would be rerouted to act on the outside of the bellows. So we're going to use IPO valves. IPO valves come in two different sizes, typically 1.5 OD and 1 inch OD. And I'm not going to talk about valve size selection, which is preferential right now. That's a whole different topic. All right, the other thing I'm going to select here is, see over on my graph, I've got this, here's my gas injection pressure line, and then I've got this additional line here. It's honoring this request here to drop the surface closing pressure to match the quantity of gas requested. So that's why that line's actually there. If I say do not drop it and apply, then that line goes away. But I want to see, so that this indicates what the amount of, with the set pressure on this valve, which has not been set yet. That's how much gas injection pressure I would need to inject 600 MCF of gas, with that much differential at that valve. All right, the next thing here is gas lift valve performance methodology. There are 3 available selections. Thornhill-Craver for live gas lift valves you should never use, because a gas lift valve is not a square-edged orifice in a meter run, which is what Thornhill-Craver calculates. Gas lift valves have flow pass through them that are not through a square-edged orifice, but the main thing is that the ball and seat in a live gas lift valve, the ball is never very far off seat, typically only about 40 thousandths of an inch of lift off the seating surface. So there is 2 different methods that calculate that, and Winkler is a a free one. I forget what the terminology for that is, but open access for that. And then this other one is trademarked. So this is Valve Performance Clearinghouse. I get an error when I try to use that because I'm not a member of the clearinghouse, so it requires an additional password to be able to access that stuff. But the Winkler stuff, the Winkler calculation methodology works quite well. In this grid right here, this is simply FYI. There's no calculations that use these numbers, but this is simply to show you that if you were going to do a annular gas lift design with 5-inch casing, 2 7/8 tubing OD, the effective diameter of that annular space would be 4.1 inches. SNAP does not use effective diameter for calculating pressure drops or hydraulics in the annular space. It actually uses the complex hydraulics from whatever method you choose, and it calculates the hydraulics based on friction on both of the wetted surfaces. So that's the OD of the tubing and the ID of the casing. So those 2 wetted surfaces and friction of the fluid flowing up there is what's the most, is the way you should calculate that, and that's the way SNAP is doing it. All right, so, but just FYI, if you wanted, guessing what the equivalent diameter would roughly be. All right, so that's some of the input information I need over there. And then on the right side over here, I have ambient wellhead temperature. And that's going to help me determine what the flowing temperatures at each valve depth are. So, and in this instance, what we mean by ambient wellhead temperature on the wellhead itself, but what is the ambient ground temperature. So, for example, my basement here in Denver is about 10 feet deep, and the average temperature year-round, summer and winter, is roughly 60 degrees all the time. So that's the number we're talking about here when we talk about ambient wellhead temperature. It's the earth temperature at roughly 10 feet. And that's where our tubulars and our hot fluids flowing up our tubulars are going to be losing temperature to the earth at that top of the well. And we're going to use the SNAP IPR that we've created before, and it happened to be using a flowing bottom hole pressure, a reservoir pressure of 2,500, and the equivalent PI at that depth is 1, but we're not going to use that. Water cut 50%, formation GUR 1,500. And here are my depths, my packer depth and my end of tubing and or packer depth, and then my formation depth, perforation depth. In a horizontal well, we typically use the heel of the well, and because that's the only place we really know 100% of the flow is going to go through. If you pick the toe of the well, then you're going to add some additional pressure, that maybe 20 to 50 psi more than the pressure at the heel. All right. And then this little toggle here is going to allow us to set our lift point at different depths. For example, I turned it to 2 and it moved it up whole. And it depends on how you've got your system set up. You can count from top to bottom or bottom to top. Depends on, it's your preference. What I've kind of found over time is that if you're running conventional gas lift mandrels in your well, then you're going to count from bottom up, because number 1 is the first one in the hole when you're running your completion. So your mandrels will typically be indexed 1, 2, 3, 4, 5 from bottom to top. But if you've got a well with side pocket gas lift mandrels in it, then we typically index them top to bottom. Number 1 is the top one, because that's the first one we encounter with our wireline tools when we go in to change out a valve. All right, so that's that. You can plot liquid levels on here, and here's another thing. So if I go back up here to edit and preferences, most of these plotting things here have to do with the gas lift graph. So if I want to show my gas lift graph, I would turn that on. So different things, and some of these things in the middle here, when we do an automated gas lift design, these are some of the defaults that it's going to choose, what type of valve, what size valve, and stuff like that. So that's how you can manipulate different things on the gas lift graph. You can make it really busy. All right, so we've got to the second gas lift valve so far. Woohoo, good deal. All right, so how would I place the third one? Transfer pressure to get to here. Then I got to pick a transfer pressure here, right? So that's roughly, something like, well, I got an XY coordinate right here on my graphs, all my graphs. So I want to put it somewhere right there, right? So I would have to go back to my input dialog, gas lift valves, and I'm going to guess, right here about, 5,200 feet. So don't know if you realize it or know it, but gas lift designs are always based on true vertical depth, and you translate those depths to measured depth to install equipment in the well. We're talking about pressures at depths in wells, liquid pressures and gas pressures. So that's density numbers. So that's primarily TVD depth versus the density number. So here I'm going to put 5,200. Push the enter key. It knows to update that because of the Wellbore description and the deviation survey. I'm going to choose a bellows valve. I'm going to choose a 1-inch valve. I'm going to choose this is the list of valves that we have in our drop-down history, I guess you could say in our catalog. And these are valves that have been flow tested by the Valve Performance Clearinghouse. So now that I'm looking at this, I can tell you about Valve Performance Clearinghouse it's actually run by the LSU petroleum engineering department. We started this about 20 years plus ago as a industry consortium. We wanted to investigate how gas lift valves actually performed. What is the throughput through a gas lift valve given a certain set pressure on the gas lift valve and upstream downstream pressure relationship in a dynamic flow loop? How much flow rate can I get through that valve? So we gathered together a few operating companies. I was the rep on the ConocoPhillips side, but we had, well, when we started, it was probably Arco, and then BP, and then Conoco, and then ConocoPhillips. What we did is we hired a consultant that was knowledgeable in gas lift valve mechanics, and we constructed a flow loop so that we could insert a gas lift valve in there and flow through that gas lift valve. We could hold the upstream pressure constant and flow through the valve while varying the downstream pressure, and then map the flow rate of basically injection gas through the valve, and then develop mathematical correlations for those descriptions. And so all of these valves and the corresponding port sizes that go along with them in our catalog here are the valves that were flow tested to date at this particular version of SNAP. You're not going to have maybe a 1-inch, well, a 1-inch Camco. That's a BK valve. That's a wireline valve. It's actually a quite poor performing valve. So what we would normally choose for a generic 1-inch gas lift valve would be this McMurray C1. Turns out over history, many of the gas lift valve manufacturers, vendors, have cloned this original McMurray valve, and that's what you're buying when you get a new valve or get a valve from a vendor nowadays. So when I do that, make that selection, and then make a port size selection, in the catalog, it also knows what that R value is. R value is the ratio of the area of the port divided by area of the bellows. And this is the thing that dates back to, well, why is it R? Well, Dr. Kermit Brown, who was the senior professor at the University of Tulsa in the petroleum engineering department. So he was head of the artificial lift group at the university, and he's responsible for a lot of the gas lift theory and practice that we use today. He's, over time, he's written 2 books, one back in the 60s, artificial lift, and then a series of 4 books, probably in the late 70s, I think that came out, a series of 4 books. But anyway, he used to do gas lift schools, and he had an overhead projector with the clear slides and a grease pencil, and he's writing all these equations out by longhand. And he said, gee, I'm tired of writing this AP over AB ratio every time. It's a ratio. I'm going to call it R instead of AP over AB. So that's what this is. This is the area of the port divided by the area of the bellows in a clone McMurray C1 valve with a 3/16 or 12/64 port. Okay? And then we're going to have to calculate the test track pressure on here. But for right now, all we're doing is setting the gas lift valve depths and their port sizes. All right, so now I've got my other one set in here. I'm going to apply that, and oh, that's way too shallow, right? I need to move that valve down. So I have the choice of increasing my depth here and seeing what that does. Okay, so that's not bad, put it over there, right? And then apply that, but I got no test track pressures here, so it's not going to give me this information here. So what I'm going to do here is push this button that says refresh and round TRO, test track opening pressure, at 60 degrees. Okay, so now I've got a TRO there, and 3/16 C1, 940. Okay, wonder why those other ones didn't change. They're supposed to change when I do that. Okay, anyway, so apply that, and then move my lift depth down to that valve, and says under those circumstances, that's what 600 MCF lifting through that valve would require. All right, so I would just continue this process, right, until I filled in all my gas lift depths. Well, that's a little tedious. Wouldn't it be nice if I could automate that thing and have snap space on my valves? Oh, by the way, you see these little data points here? That's it's actually a flowing survey that I've got in this particular data set. I don't remember why I put it in there, but it's because of this data right here. So any data on the pressure survey or match data point shows up on any of the graphs that have pressure versus or liquids and stuff in the graph. Depth versus pressure, pressure versus rate. All right, so I just put in just FYI. All right, so spacing mandrels. We continue this process, right? Till we got, look what happens as I get down here though. When I pick my transfer pressure here, put that valve in there, it's going to be at what, 7,200 feet or something like that. Maybe. A little deeper. Okay. It looks sort of good, right? I pick my valve types. Like RC1, 3/16, apply, set the pressures, apply, okay. And I would continue that, but notice that my spacing is getting shorter, getting closer together, each deeper mandrel. The next one's going to be really close, all right? So I may not want to do that. In fact, it's impractical to do that in a modern unconventional well. What I want to do once I get to a point where my mandrel spacing is starting to get relatively short, I want to fix a bracket spacing from this point down to the end of my tubing. Common spacing numbers are, for a conventional well, I'm going to say 500 or 600 feet. For an unconventional well, I'm going to say something like 800 bracket spacing down here to get from this valve downhole. All right, so that's what I would start doing then. I would add 800 feet here and add 800 feet till I got my whole design fleshed out. Like I said, kind of tedious, right? Okay, how about this? Let's do it with the help of the computer. Here's the magic button right there, basic mandrel spacing, okay? It gives me this new input dialog. It wants to know what my liquid rate is, what my injection gas rate is, what's my maximum lift depth, and in this particular case, it's let's say 9,000 feet, okay? And I want to take, remember I have to, gas lift theory, I have to take a pressure drop at each deeper valve to be able, so I can close those valves as I move my lift depth deeper in the well. And then down here at the bottom, my spacing is getting really, really close. So I'm going to say I'm going to default to some spacing. This one I got, it's relatively shallow, so there's 600. I like that 800 foot number. So that's what this checkbox says. It says even if I couldn't space another mandrel at that depth, go ahead and space mandrels from whatever stopping point where it starts getting less than 800 feet. Space them at 800 feet anyway. And over here it says try to keep or attempt to maintain this delta pressure from the objective liquid gradient to the transfer pressure. I want to maintain a 20 psi differential there. And then I'm going to space the second mandrel into the same gas injection pressure as it's shown here, because when I uncovered that valve during the unloading process and started injecting gas here, this valve is still open initially, so I still have this much pressure available. All right, so we'll do that. And then all I have to do here is watch the graph, and there we go. Do that a couple of times, and it stopped right there at 9,000 feet. Now, that's pretty shallow, so I might want to adjust these depths a little bit. I can do that quick and easy. If I was doing this on graph paper, doing it manually, I'd have to go back and change all my depths, start a whole new graph up. So let's say what does 750 look like? That's a little better. I got all these operating valves down here spaced pretty good. I'm going to say if I'm happy with this, right? I might go through several iterations of this. I'm going to say I'm done. Sorry. So when I push that done button, Snap populates the gas lift valve detail grid with all the valve depths and port sizes and stuff that was on that preferences elected, right? This stuff here. All right. So it will also do this. It likes to think it's smarter than you are. So it says, look, with the Mendel spacing and pressure drops and set pressures you put on all these valves, I'm going to have to lift it. I can only lift right here, right? But I've got another valve down here, and actually this would probably be like end of tubing, right? So what I would do here in this case is I'd change that back to a bellows, back to a C1, and then I would pick an orifice valve for this location. So, and if I pick other, look what happens here. I get this list of all those different available port sizes. But if I pick a actual orifice valve here, like the Altec valve, and then drop this down, those are the only selections I have for orifice size. But because we have that particular valve and its flow correlation in our database here, we can select an actual port size to use here. So if we pick that Altec valve with a 1/4 inch port and then reapply here, did you see this line move? All right. If I change that port size, put a small one in there, this is that drop the gas injection pressure to match the desired gas injection rate here, which in our case is 600 MCF. It's calculated there, the differential required through a 3/16 orifice to inject 600 MCF of gas if the flowing tubing pressure is equal to 980 PSI, which is that point right there. Okay, so if I wanted to put or investigate a different port size, so here's what a 1/4 inch port would look like. Watch this line. Did I do it? Yeah. Oh, it's still fixed on that. It's fixated on that on that live valve right there. And I don't have enough gas injection pressure to make it go down there. Okay. So I can move my lift point up and down. There we go. Okay, now I've got it on the orifice. All right, so now I can show you. That's with a 1/4 inch port. Very little differential required. If I put a smaller port, watch that line right there. It's okay, now you need this much differential because you got a 3/16 port, you're still injecting 600 MCF. That's still the flowing bottom hole pressure predicted from our hydraulics curve at 600 barrels a day. So now I need that much differential. That is actually shown on the gas lift output report, which is here. And it's telling me what the surface closing pressure of the bottom valve is in this top paragraph. But here's that orifice DP right there, 163. So if I change that to a 1/4 inch port and reapply that, watch that number change. That's the differential now with the 1/4 inch port in there. The other information on the output report is all the input information we requested, all of the valve depths, whether it's a bellows valve or an orifice valve, what valve model it is, what port size it is, what is that R ratio, R, the AP over AB ratio for that valve. And this column says P sub PEF, pressure, performance, effect, factor. Oh, no, sorry. Yeah, pressure, yeah. Tubing effect factor is what it should say. So this is the AP over AB ratio divided by 1 minus the AP over AB ratio. In other words, R divided by 1 minus R. This tells you the percentage of opening force that comes from the tubing pressure. And then, of course, it reports all my temperatures that I have here. And when we're doing a gas lift design, that's a very important part of the set pressure calculations. A gas lift valve is a fixed volume pressure chamber. Inside that bellows, inside the dome of the valve, we have a nitrogen gas in there as the temperature changes, that set pressure will change. So we set the valves up in a workshop at a fixed temperature. We have a temperature control bath there that the valves are cycled through and then put in the test rack and brought to set at the exact pressure. When we put those valves in the well, they're going to operate at what we have calculated as the flowing tubing pressure at the gas lift valve depths. So what we must do is we have to calculate best we can what those set pressures are, or what those temperatures are, sorry. So here's a little utility right here, detailed temperature options. And the best correlation, or really the only one available right now for calculating this, is by Dr. Beggs and a grad student named Shui, S-H-I-U. So what this does, this uses that ambient temperature I talked about earlier at the wellhead, 10 feet below, and all the PVT properties of all the fluids, the flow rate, the API gravity, the reservoir temperature. So it's calculating how fast that fluid's moving up the wellbore, and it's calculating a temperature at surface and a temperature at each gas lift valve. So push that button, you say, okay, plot those temperatures over to my gas lift detail information here. So there are my gas lift valves now with those temperatures. So now if I'm done. If I recalculate that and reset those valves, now they're set at these temperatures to operate with these temperatures downhole. So what happens over here, the output report says, okay, well, you just changed all the temperatures and now it's not honoring that. Okay. Test track pressures. Oh, it finally did. I had to click it a couple of times. So now my test rack pressures are set up for these valves, this port size, and this downhole operating temperature at each valve depth. So here are some of the detailed calculations of our gas lift installation. So here's all the details. Here's your production pressure at depth. Most of the acronyms are API, gas lift, recommended practice acronyms. So, for example, PPD, production pressure at depth. PWF, pressure well flowing. That's at a depth also. But typically, if it says a uppercase letter, a P being a pressure, if it's got a D in the acronym, that means it's a downhole pressure. If there's no D, it's typically a surface pressure. And certainly down here, this is the output information. So based on this PTRO 60 column, here's the set pressures on the valves. We've chosen a 30 psi surface closing pressure drop for our valves, and that's the API recommended practice for gas lift designs using surface closing pressure drop methodology. That's what SNAP does. So here's PSC, pressure surface close. Now, that's the acronym that most of the industry uses. The API acronym for this is actually PVCD. This is PVCD. This is the downhole closing pressure. This would normally be PVC, but because industry standards, all of the vendors use the acronym PSC, indicating pressure surface close on the gas injection pressure side. So that top valve closes at 921, and then we purposely have set these at a 30 psi decrease. So the next one is 30 psi less is 891, 61, and so on. So those are the surface closing pressures that when you go out to the well, if the well's operating at 600 barrels a day, 600 MCF injection gas, injecting at the bottom, then these are the gas injection pressures you should see at the surface. The gas injection pressure you see at the surface is related to that surface closing pressure and ends up being very close to that, just slightly above that. The other things here important for gas lift design are this is the temperature correction factor that's used to correct the bellows pressure, inside the bellows pressure from downhole temperature to shop conditions. PIO, pressure, injection, opening. That's at surface. So this describes what the opening pressure at each gas lift valve would be if the flowing tubing pressure were equal to this, to the transfer pressure. So gas injection pressure at surface, opening the valves if the transfer pressure is there. Now, one other thing we can do with SNAP is we can interrogate an existing design. This column is editable. So I can actually go in here and change these to whatever I've actually installed in the well. On the output report, you'll see these two columns, the test track 60 and the test track installed. This will be what we've actually installed in the well, and then this is the numbers that SNAP is saying you should set the valves up for all the conditions that we've put in this data set. But by doing that, we can go in here with whatever valves we have and whatever sizes we'd tell it whatever those were, but with the actual test rack pressures, not what SNAP says. So then we can go to this troubleshooting tab up here. And what this does is it looks at valve set pressures and if the flow rate's different, well, then the temperatures are going to be different. So we'll update those temperatures as well as updating the test track pressures here when we do this troubleshooting analysis. And then it's not going to use the transfer pressures as the tubing pressures. It will use the actual flowing tubing pressure off of our objective liquid gradient curve. And it's going to recalculate all the surface closing pressures, and it will calculate the gas throughput volumes for all the gas lift valves using whatever model we chose. So the one that's going to be active here, or accurate here, the one's going to calculate against the 600 is going to be the Winkler one. So when I push, now all I have to do is push this auto match button here, and it will do all those calculations in like the blink of a second. So do it a couple of times. So now what you see is it says, okay, really what's going to happen if you run this installation and it's producing 600 barrels a day and you've got all those valves set at these initial test rack pressures, and the temperatures are now at the new, if the temperatures are different than they were, then this is what has to happen. Here it's looking for the gas injection rate. So here's what I've told it. I said I want 600 MCF here. So it's going to try to match that up using the valve performance information. So I did it a couple of times. It finally resolved to 600 here. So it says, well, what's going to actually happen is this well is going to multi-point on these two mandrels here. This valve can only flow 348 MCF at this tubing pressure and at this gas injection pressure. But at this gas injection pressure, this next valve is also open, and it's going to be at the set pressure it's at. This pressure is required here. It's going to be flowing 251. So it runs that complex math, calculating, moving that gas injection pressure around until it sums up our desired gas injection rate. So if I change that to, say, 800 and say now auto match it, now I've got 3 valves open. So I actually got around bottom by increasing my gas injection rate. But, with that port size, it's not generating enough gas through that bottom orifice, so it's still opening these upper 2 valves. So that's how you use the troubleshooting thing to figure out what our actual operating conditions are going to be. All right, Jessica, I've run out of time, it appears. There are probably some other things in here if we want to do some, what was this introduction to SNAP, right? Not how to do gas lift design with SNAP. So that would take a few other hours. Okay, so are we done?
Yes, thank you so much, Tom. Thank you. And I'm sure there's going to be lots of questions from people afterwards, so feel free to send us an email. And Tom, we thank you so much for this course. I know lots of people have been asking about the recording. We will make that available afterwards, so I'll send that out to everyone.
And sorry for my voice today. I actually tested positive for COVID from my trip to, where did I go last week? I went to Midland. Yeah.
Tom, you were a champ. Please make sure you drink lots of tea and honey today and rest up that throat.
I'm going to do that. Okay, we're going to sign
Wonderful.
off.
Thank you so much, everyone. Take care.
All right, goodbye.